First question is on probability and statistics. So as usual with those kinds of probability questions, we start with the distribution. X is a random variable. It has the so-called zero inflated Poisson distribution. So zero inflated maybe reminds you of the assignment, right, where you had a zero inflated geometric. In the present case, it's a zero inflated Poisson. What this means is simply this. It's a Poisson, but the probability of a zero is made higher than it is for the regular Poisson. So then this distribution has two parameters, Q here and lambda. Now lambda, you can kind of view it as the usual lambda parameter of the Poisson, but this distribution is just a bit more complicated. You see, the probability of a zero is this expression that depends on both Q and lambda, and the probability of any other value, any K that is not zero, looks like that of a Poisson, because K here, this part is the same as the Poisson, but then it's multiplied by the constant 1 minus Q. Okay, so that's the distribution we will use. It's obviously a discrete distribution. But now the specific context is, again, Josephine, our friend from our usual friend. She's using dating apps, and it happens that the number of first dates she gets from using the dating apps has the zero inflated Poisson, right? So you can say X, the number of dates she has, first dates in a given week, as the following distribution, which we call ZIP for short, zero inflated Poisson. Okay, and obviously this distribution has those two parameters then that in general are considered unknown, but then later in the question we'll give you specific values for them. Somebody asks in the chat, what's the best revision method for the final? Hard for me to say because studying methods maybe they vary from person to person. I would say don't neglect studying the actual slides, like the lecture slides with all the content. I would really make sure you master everything in the slides, all the formulas or the exams, so like you conceptually understand every formula. After that, you do lots of practice, right? Practice makes perfect. So once you master the theory, I would do lots of practice problems. You redo all the tutorial problems to make sure you master those, and then you do the past paper questions. You focus specifically on 2020, 2021, 2022 past papers and quizzes, because I wrote those. That's already a lot of work. If you have time after that, you can do the older papers as well. Yeah, but my only small advice is, yes, practice is super important, but I don't think it's the only thing you should do in your studying. Like I think some students just jump into doing practice straight away without first having mastered the theory, like the lecture content. I think that's a mistake, because then when you do practice, you might be a bit lost and you see a question, you don't know how to do it, and you're not sure if it's because you don't know enough theory to be able to do the question, or you just don't see how to solve the specific question. You see what I mean? So I think only once you've mastered the theory, then should you do lots of practice. At least that's how I used to study when I was a student, and I would usually do decently well, but everybody is different, I suppose. Maybe some people really need to do practice to understand the theory, and then once they've done practice, they understand the theory, they can go back to doing more practice, and it's more of a cycle like that. You read the theory, you do some exercise, you understand the theory better, you go back to it, you reread the theory with updated understanding, and then you do more practice. I don't know. Okay, now thanks for your question, but back to the problem. Part A is kind of a pure probability question. Assuming the number of first dates per week, that would be generically denoted X, are independent from week to week, right? So having lots of dates in week 1 doesn't change the probability to have dates in week 2 and so on. What is the probability Josephine has at most one date in the next 4 weeks? Okay, now we don't give you specific Q and lambda values, so you need to express your answer as a function of both Q and lambda. Now here, the solution is there. Conceptually, you need to realize that, okay, at most one means two distinct and mutually exclusive things. Either she has 0 dates, okay, in a space of 4 weeks, or she has exactly one date, right? So exactly 0 and exactly 1 are two mutually exclusive events. So if you want the probability she has 0 or 1, you would sum this plus this, right? And they're mutually exclusive, right? So obviously you could subtract their intersection, right? Well, D0 here and D1, but their intersection obviously is 0, right? Now, probability that she has 0 dates. Now, careful, remember it's in a space of 4 weeks, right? In a space of 4 weeks. The probability of that specific event is not too hard to find. You just imagine that you have those weeks here. You can view them as spots you want to fill. And specifically, she has 0 dates the first one, 0 date the second week, 0 date the third, 0 date the fourth, right? But number of dates per week are independent events. So this would be the probability she has 0 date one time times the probability she has 0 date again, and then 0 date, and then 0 date, right? So it's the multiplication of P0, 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 P0 4 times. Okay, so, and obviously the probability of a 0, the probability that poor Josephine has 0 dates in a given week is this number there, okay, which is replicated here. It's only that now it has a power 4. So that's not too bad. Let me know in the chat if you want me to explain this again. Now you need to be a bit careful with probability she has exactly 1 date, because if again you visualize dates or dates in given weeks like this, that's four weeks you want to fill with a specific number of dates. Well, there's more than one possibility for the overall event. She has 1 date, right? Because she could have 1 date in the first week and then 0, 0, 0. But that's one specific case. She could also have 0 dates in the first week and then 1 date 0, 0, and so on. She could have 0, 1, 0, and then she could have 0, 0, 0, 1. So all of those cases mean or are sub cases of what we're interested in. The case in this instance, exactly 1 date in 4 weeks. So basically you need to sum those 4 probabilities, okay, or you multiply the probability of one of those configuration by 4. Now, one of those configurations here, or allocations, as the probability as given there. Well, yes, because for specifically 3 weeks she has 0 dates, and then for exactly 1 week she has 1 date. Okay, so in total the probability will be P0 times P0 times P0 times P1. And then if you've understood this, you've essentially solved the problem. Obviously, P0 is the same expression as before. Now it's power 3. And then P1, you also grab the P1 from the general expression given here in the second line of the general equation for the PMF. Okay, this thing, I think it's clear, but this one is valid for any k, right? So if you have k equals 1, you just plug 1 here and 1 here, and you have your probability. Okay, well, I mean, 1 factorial is just 1, but we left it there as 1 factorial to make it clear where it's coming from. And that's it then. The last step is just to put everything together and make a little bit of simplification, although here, unfortunately, it doesn't simplify that much. If you add this one and this one, you can put this term in front, but it will be to the power 3. And then for the first term, you'll have this term replicated. And then the other bit will be the 4 that is here. Sorry, the 4 here, and then this part. Okay, and after that, you look at this, and I don't think you can simplify much more. I don't think there's meaningful simplification you can make. Okay, so you're left with this relatively long, ugly expression. Okay, let me know if you have questions. Otherwise, we go to part B. I'm trying to zoom a bit more, but not too much. Okay, that should be fine. Each time Josephine gets a first date, there is a 25% chance it leads to a second date. Okay, so every first date is it leads to a second date, but only with probability 25%. And now they also remind you or tell you independently of the success of other dates, right? If she starts dating somebody like a second time, but she might also date somebody, she can go on multiple dates in parallel. which is fine. We're not here to judge what Josephine does with her life. We're just analyzing the situation. Now, given that, what is the expected value of the number of second dates? Okay, so now we're interested in the second dates that she gets in a year, so in a whole year. Now, that looks a bit harder, but at least they give you a hint. They start by finding expected value of x, because so far we don't know what expected value of x is. Remember, x is number of dates, number of first dates in 1 week. Okay, because every first date leads to a second date with chance 25%, and we want the overall average in a year. Looks like one of the main ingredients we need is the expected value of the number of first dates, right, in a week. So let's start by finding that, and after that, it shouldn't be too bad to find the expected value for a whole year. Well, actually, we can already do it, like in the sense that in a whole year, there's 52 weeks, right? So 52 times expected value of x, that's the expected number of first dates in a year. Now we're interested in the number of second dates, but second dates, they're lower by a factor of 1/4, right? There's only 25% of first dates that gets converted to second dates. So intuitively, it should be that the final answer will be this times 0.25. Now this is a bit like it's probably not rigorous enough. We can do the actual formula, law of total expectation, to get to this answer, but it seems intuitive that the answer will be this. But then to get to this, we first need to find E of x. So let's do that. E of x is not too bad. You can start with the general formula. That's general formula. You start at 0 because indeed 0 is possible. But now realize that the first term in this sum has a k equals 0. So obviously the first term doesn't do anything. So you might as well start the summation at 1, right? I mean, it would be this plus 0, right? So you might as well start at 1. Now, what's practical then is that the pk's for k equals 1, 2, blah, 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 they all have the same expression. In your statement of the question, it's only the first case that is different. All the other cases have the same general expression for their probability. So now you can just plug this formula inside the summation, okay, which is done here. Okay, with k left as k. Then the constant 1 minus q, you can put it in front. And then you're essentially done, because if you look at this term, the summation, well, you should realize it really is just the expected value of a regular Poisson, right? Not a zero inflated Poisson. It's the expected value of a regular Poisson. Now, careful that you might say, shouldn't we start the summation at 0 if it was the expected value of a Poisson? Well, yes, but the term 0 doesn't do anything, right? You could start this at 0 because the first term 0 doesn't contribute anything to the summation, right? So the fact you start at 0 or 1 doesn't change anything. Okay, so because of that, yes, indeed, hopefully you agree that this part is nothing else than the expected value of a regular Poisson with the parameter here, a lambda. Okay, and that's quite nice because, well, you know that the theoretical expected value of Poisson lambda is just lambda. Okay, so overall quite easy. You have expected value of x is lambda. That would be the expected value of a regular Poisson, but multiplied by this factor 1 minus q. Okay, so obviously the expected value is lower than what it would be for a regular Poisson, which makes sense if you remember that this zero inflated Poisson is like a Poisson, but we've boosted the number of zeros. If we boost the number of zeros, or the probability of a zero, I should say, was going to decrease the expected value. Okay, then, as I said, what we're interested in is the number of second dates, right? And here we denoted here big N. Now those second dates stem from all the first dates, right, obtained in a year. Now you can denote, okay, the number of first dates, right? Number of first dates, because you count for every single week how many she had, how many dates in week 1, how many dates in week 2, and so on. So you're counting all the number of dates, well, first dates. And what we're after is e to the n. Now, as I said, intuitively, I think it makes sense that you should have 52 times e of x and then times 25% because every date leads to a second date with chance 25%. But a bit more rigorously, you can use your law of total expectation, right? You could say that knowing that or given that the number of first dates is whatever, little x, okay, given that the sum of all the number of dates is little x, then the number of second dates will be a binomial. It will be a binomial with number of trials, little x, right? How many first dates she got, and probability of success, 0.25. 0.25 as given in the question. So you have a number of trials. Those are all the first dates she had. Every single first date leads to a second date, but only with probability 25%. So indeed, this corresponds to a binomial. And it's quite easy because you know that expected value of n given x is just x times, well, p, probability of success, right? X times 0.25 here. Okay, so you can say expected value of n is expected value of n given x. That's the formula of the law of total expectation we've used lots of times. And an expected value of n, if you know this, okay, given the number of first dates, will be this times p, probability of success. And then you're done. Pretty much expected value of this whole sum would be 52 times the expected value of 1. 0.25 is a constant, it's in front. And then you get this, which is exactly what I said before. You could probably have guessed from the beginning this would be the answer. And that's it. I mean, you can simplify 25% of 52 is 13. Okay, that's the bottom of this question. Let me know if you have questions. Then we can go to part C, which is we now enter the statistics part. And here, to simplify our life, we will assume that from now on we know Q is 0.3. Okay, so Q is no longer an unknown parameter. Q is known to be 0.3, and the unknown parameter is then lambda. Also, x1, x2, blah, blah, blah. As usual, they denote an independent sample of whatever random phenomena you observe here. X1, x2 would be the number of first dates in any given week, right? X1, number of first dates in week 1, x2, number of first dates in week 2, and so on. How we obtain this information, I'm not too sure, right? Maybe you've been stalking Josephine, or maybe she posts all her dates on TikTok, who knows? But here we just assume you have the information. Okay, first question is propose an estimator of lambda. And well, now the solution is there already. Now, remember what was the logic of finding an estimator of lambda in the case of the good old regular Poisson, right? In the case of the good old regular Poisson, in class we said something like expected value of x is lambda. Now, this is theoretical, this is near theoretical, but I can approximate my expected value of x, which is theoretical, I don't know it, by, I can say this should be roughly equal to the x bar, right? The empirical average, right? The sample mean. And if that's the case, well, I'll approximate lambda by x bar, and then I'll say that my estimator of lambda is x bar. Now, this logic applies here. You just need to be a bit careful. The relationship has changed just a little bit. Now you have expected value of x is no longer directly lambda. It's a constant times lambda. But this constant here, it's assumed to be known, right? So you assume that you know q is 0.3, so 1 minus q will be 0.7. So you have the relationship e of x is 0.7 times lambda. So then you can obviously say lambda, theoretically lambda should be expected value of x divided by 0.7. You don't know the theoretical expected value of x. By you don't know it, I just mean you don't know the numerical value, right? That's the whole point. So then you need to estimate the theoretical expected value. You estimate it by the sample, the empirical average, x bar, and that's it. Your lambda, your estimator of lambda will then be your estimator of x bar divided by whatever this constant is. And then by a straightforward calculation, lambda is unbiased. Well, of course, because well, we can do it, but expected value of lambda hat is going to be the expected value of this. You can put the constant in front, 1 over 0.7, then expected value of x bar. But as you know now, hopefully, you know that expected value of x bar is just expected value of x. It's the same thing. Okay, and then of course, expected value of x is 0.7 lambda. So the 0.7s obviously cancel out and you get lambda. So your estimator is indeed unbiased. And it's happy days. Okay, the solution also tells you the variance diminishes as n increases, which is a good thing, right? As you get a bigger sample, you should have the variance of your estimator decrease. And that's the case because, of course, the variance of x bar is the variance of x divided by n, right? So this, of course, diminishes with n, or it even goes to 0 when n goes to infinity. Okay, let me know if you have questions about that. Otherwise, we go to part D, which is the hypothesis test question. Now, part D is conceptual. In this context, now you want to test a specific hypothesis. For some reason, you want to test the hypothesis lambda equals 2. That's the null hypothesis against the alternative. Lambda is strictly smaller than 2. Strictly smaller than 2. To do this, explain why the choice of test statistic T, that would be the notation for the test statistic, but here in this case, T equals the sum of the x's. Why is it an appropriate choice? Why would you, as a test statistic, to evaluate those hypotheses, why would you choose the sum of the x's? And then second question is, or second part of the question is, for what types of value of T would you reject H0? Would you reject for small values, large values, or both? Would you reject for both? Maybe I'll ask the chat, because I've been talking so much. Maybe the chat can be a bit more participative and let me know what is the logic of using this T, just in words. Okay, while you think about this, I'll take my hoodie off because it's getting very hot in this office for some reason. That's better. So yes, I'm just waiting for, or expecting a small explanation, just a few words. Okay, now I see there's now 12 people in the chat or in the live lecture, which is good. We don't have an answer yet, but we do have a worried emoji, which is sad. Okay, well, it looks like the people in the chat, maybe they're too shy to share their answers. Let's try to understand the logic of well, what's happening here. So remember, X is the number of the number of dates she gets per week. Now, the average or expected number is 0.7 lambda, right? But said otherwise, expected number of dates is directly proportional to lambda, right? If lambda is large, it means we expect lots of dates. If lambda is small, well, we expect fewer dates. Yeah, Jovan says small is the answer for the second part of the question, right? Yes, then that's correct. We will reject H0 to accept H1 for small values of the test statistic. But now the first part of the question is simply to explain the logic of using T. And we don't expect anything too complicated here. We just want you to realize that we test that lambda equals a specific value too, right? Now, big lambda means she gets lots of dates. Okay, and small lambda means she gets not many dates, right? Now t is just the sum of all the dates, all the number of dates she gets, right? If she gets 3 dates in n weeks, well, t will be 3. If she gets 10 dates, well, t will be 10, and so on, right? So t puts together all the evidence you have for or against a given lambda, right? Lots of dates or not lots of dates, right? So the logic is, if lambda is big, t will tend to be big. If lambda is small, t will tend to be small. And I mean those things in relative terms, right? What is big, what is small, it depends, right? But I just mean conceptually, bigger t indicate a bigger lambda, and small t indicate a smaller lambda. So here, if you're interested specifically in testing that lambda is a specific value against the fact that it would be smaller, well, it makes sense that if t is small, you will tend to reject that specific lambda. So that would be the answer, right? T puts together all the evidence you have for or against a given lambda, but specifically if t is too small, you will reject that that lambda is a specific value to accept that lambda is actually smaller than that value. Hopefully that makes a bit of sense. And this would be written in this text here. Okay, that's kind of conceptual, but now we actually do the calculation. So in part E, we give you some numbers. Okay, so you've actually observed that Josephine, in a space of 4 weeks, she didn't have too many dates. In fact, she had 0 dates the first week. She had 1 date the second week, and then 0 dates, and then 0 dates. So in a space of 4 weeks, she only had 1 date. Now, that seems quite low, but can you reject formally using the statistical test methodology? Can you reject H0? Now let's just go back here and have a think. This is given in the question. In the solution here. The expected value of t is 0.7. It's 0.7 times n times lambda. Well, yes, because t is just the sum of n times x, and the expected value of x is 0.n lambda, right? So in the specific example here, t is actually 1. T is only 1. But the expected value of t, if h0 is true, would be 4 times the expected value of x, and the expected value of x is 0.7 times lambda. Now, lambda specifically under h0, what we're testing is 2, right? So you get 2. Now that's what the value of this would be. 1.4 times 4, 2.8, 5.6. If I didn't mess up, should be 5.6. So you see, we're way off, right? Like we expect if h0 is true, we expect 5.6 dates on average in 4 weeks, but she only got 1. Now, so it does look like lambda might be smaller than what we think. It might look that h1 might be true, right? But do we have enough evidence to actually reject h0 and accept h1? So let's see. You need to do the calculation, and of course the p-value calculation, because the p-value gives you quantitatively how unlikely are your results under h0. Like if h0 is true, how unlikely it is that you observe the actual numbers you observed. So let's explain the first line. P-value, recall, we will reject if t is too small, right? So the p-value will be the probability your test statistic is smaller or equal to what you've actually observed, right? What you've actually observed here is, t equals 1. So you want to find this probability that t is at least as small as what you've indeed observed, but under h0. So assuming h0 is true, how likely it is to have observed 1 date or fewer. Now, luckily, this calculation, we've actually done it. That was the part one. In part one, we've done exactly this. We've computed the probability that in a space of precisely 4 weeks, she gets 0 dates or 1 date. That's exactly the calculation done in part one. So that simplifies our life because we can just grab this formula. So this is the formula that I called ugly before. Okay, that was the result of part one. It was exactly this calculation. She gets 0 dates in one week or 1 date. So using this good work we've done before. This is really a replication of the formula, but now we have specific values, right? We of course, the question tells you Q is 0.3, and we are specifically under the hypothesis that lambda equals 2. So you can plug lambda equals 2 everywhere there's a lambda. And that's it. The rest is just plugging everything in your calculator. And in fact, you get something that maybe is slightly surprising. You don't reject, right? Because the p-value, yes, is not a big probability, like 7% or so, but it's not that unlikely. So it's not that unlikely she would get only 1 or 0 dates if lambda is actually 2. So because this probability is not too small, it's not smaller than significance level, your conclusion is you do not reject H0. Right? So even if on average you expect 5.6, it's actually not that unlikely that you just only 1, that you get only 1. And you don't reject. Okay, let me know if you have questions. If not, I'll go to the next one, which is a financial mathematics question. Okay, this one, I think it's a pretty good question because there's kind of, well, the question is a bit long. Like you need to make sure you understand all the context, and then to solve it, there's kind of 2 steps to do. One is about present values, and the other one is about accumulated values. So I think it's a good revision question. Okay, but now let's go over this context. Patrick has 300K in his superannuation account, right? Now, superannuation account, just think of a regular bank account. That's money he has in the account that might make interest. He also has a salary of 200K per year. Now, tired of the senseless struggle to keep climbing the corporate ladder, well, that's a bit dark, but okay. Patrick is no longer trying to impress his boss and hence does not expect any salary increase in the future. That just means that for the question, you can assume he makes 200K per year forever, right? That's his salary forever. Lucky for Patrick is employer contributes a generous 17% of his salary before tax to his super account, paid at the end of each year, right? So at the end of each year, Patrick gets 17% of his salary paid into his superannuation account, but subject to a standard 15% tax on contributions, right? So thank you, government. Now, I haven't spoken about tax in this course, but don't worry about it too much. This just means the contribution he gets from the employer that lands in his account will be 17% of his salary. His salary is 200K, but the government takes 15% off. So what actually lands in his account is only 85% of this, right? So then you need to multiply by 85. Okay, because again, daddy government takes away 15%. Okay, also Patrick makes no extra contribution to a super fund. So all he gets is what his employer is paying out. Okay, and the effective rate Patrick earns in his super account is 5%, right? So 5% per year effective. So you can assume every single year he's making 5% more on whatever is in his account. Obviously, as time goes by, he's going to get more and more in his account because accumulation, the contribution will accumulate. Okay, now Patrick will retire in N years. Okay, and N here is the unknown in the problem. What we want to find is N. So Patrick will retire in N years. N is an integer. Now at time N, the very last yearly employee contribution will be made to his account. That makes sense. Contributions are paid at the end of the year. He retires at time N. He gets his last contribution, and that's it. Then he's retired, and he can enjoy his life in Bali or something like that. But now his plan for retirement is this. He wants to be able to withdraw from his account 100K, careful here, at time N+1. So for some reason, the first withdrawal will not be at time n when he retires, it will be at time n plus 1. But then 2% more at time n plus 2. Then 2% more at time n plus 3, and so on. Each yearly withdrawal is 2% more than the previous, which in real life makes sense. There's inflation, so maybe he wants to withdraw more money as time goes by because of inflation. The last withdrawal will happen at time n plus 30. So careful here. First withdrawal at time 1 and last withdrawal at time 30. So in total, he's going to withdraw from his account 30 times. Okay, after that, who knows? Maybe he doesn't think he's going to live after that, or maybe after that he goes on the government age pension. For the question, we assume only 30 payments. I mean, 30 years of retirement is a pretty long time. Not bad. Okay, now finally, what is the question? What is the smallest integer time at which Patrick can retire? And to help you a bit, we give you a hint. We remind you what the geometric formula is. Well, the sum of the terms in a geometric progression, so the sum of r to the k, where k goes from 0 to n minus 1, will be this expression. Now, as I said, this question looks hard, but you need to realize if you break it down in two parts, it's not so bad. You first need to answer the question, okay, how much does he need to fulfill his retirement plan? Because you don't know, right? You just know what his retirement plan is, like 100K the first year, then 102Ks and so on. But you don't know how much money does that mean he needs to have at time n when he retires. So the first step is to find that. And after that, you can find n that is needed for him to accumulate all that money. And as usual with those, I'll review the solution, of course, but as usual with those questions, if you do a timeline, it might help you quite a lot to understand what's going on. Like there's a certain time n that is unknown, that's what we're trying to find. But then he starts, let's say that now it's time 0. At time 0, he has 300K. I'll write just 300, okay, but here 300 means 300K. He has 300K, but also at time 1, he's going to get C, the contribution from his employer, right, to his super fund. So he gets a payment of C. At time 2, he gets a payment of C as well, blah, blah, blah. Those C, they don't increase because he doesn't get any salary increase. Now, this is accumulation then, right? He's going to accumulate all those amounts up to time n, right? The 300 also accumulates at 5% interest. Eventually, he's going to get in his account this amount that in the solution they call Bn. But now Bn is what funds his retirement, right? So what's going to happen next is that at time n minus 1, he's going to withdraw 100K. Now at time, n plus 1, n plus 1, he withdraws 100K. Then at time n plus 2, he withdraws 102. I'll just write the 100 here without the K. Now careful, it's cumulative, right? So at time n plus 3 is going to withdraw 1.02 times 102. Okay, this will be 1.04, 104K is 0.04, and so on, blah, blah, blah. At time n plus 30, he withdraws the last amount, which will be 100 times 1.02 to the 29. Yeah, careful, because the first increase of 2% happens at time 2, right? So at time 30 is going to add 29 increases, not 30. So that's what's happening. So first step is finding Bn. How much does he need to fund all those payments, all those withdrawals? Well, let's write the equation, right? You want to find the present value. But now careful, present value, but assuming that we are at this time, right? So at that time n, what's the present value of this payment of 100? So you discount it of only one period, right? Because from the point of view of time n, the first payment of 100K is only one period in the future. So you need to discount it of only one period. This payment of 102K is 2 periods in the future. So you need to discount it of 2 periods, right? So the factor here for discount is v to the 2. This one is v, and so on. Okay, the last one is the discounting is v to the 30. I think you remember by v, I just mean discounting, right? 1 over 1 plus I. Okay, 1 over 1 plus 0.5 in this specific problem. Okay, so this is what is said here. We find the present value of all those payments. There's 30 of them. Now, if you think about it, the present value of each of those is given by this formula. Well, yes. Careful that if K starts at 0, so you're summing 30 payments here, but if K starts at 0, the first one will be discounted of 1 period, right? Because it happens in one year. But the Kth payment will have increased of 1.02 to the power K. So 1.02 is this increasing factor, right? The first one is 100K, but then the second one is 102K and 104.04K and so on. But the first increase happens, happens to the second payment, right? Not the first one. The first payment is 100K, only the second one has an increase of 2% and then so on. Okay, so that's why you have a K here, not a K plus 1. Okay, now if you look at this, you can almost use your geometric formula. It's just that you would like to have K here and K here, not K plus 1, but that's fine. One of those V's, right, you can put it there, right? So maybe I'll write this explicitly just to make sure. This is the same thing as 100K, but then I'm adding a V. Okay, one of those V's, I'm adding it outside the sum, and then the rest is fine. I will have V to the K times 1.02 to the K. Okay, the index has not changed, it's K 0.29. And then you're happy because this is also just V times 1.02 to the K. And then you can use your geometric formula. Exactly, right? This bit here, V times 1.02 is the R in the formula because it's to the power of K and everything else matches. So you start at 0, like you start at 0, and you stop at whatever, n minus 1. Well, n minus 1 can be whatever, but for us, careful, if we stop at 29, and this is n minus 1, it means we have n equals 30. Okay, explains the 30 here, which matches the n over there. And here, 30 here. Okay, and well, the R, okay, V times 1.02 is this, right? Because remember, V is just 1 over 1.05, which is good. The rest is plugging all those numbers in your calculator, and you get to this number, okay? Slightly less than 2 million. Slightly less than 2 million. Yeah, it's a relatively high number because he has a fairly ambitious retirement plan, right? He wants to withdraw 100K, then a bit more, then a bit more, then a bit more for 30 years. Oh, it's going to take him quite a bit of cash to be able to do that. Almost 2 million. Somebody asked, why is it V to the K plus 1 instead of V to the K? Well, because K starts at 0, right? And the first payment happens 1 year from time n, right? So we are at time n. The first withdrawal does not happen at time n. It happens at time n plus 1. So the very first discounting factor is not 0. There's the first withdrawal is already discounted of 1 period. You see? Well, let me know if that's not clear, but the question tells you, although he retires at time n, the very first payment he gets is at time n plus 1. So it's discounted of 1 period. But thanks for your question. That will be less though if it's next year. Yeah, but this is a present value problem, right? We find the present value. So indeed, the present value of the first payment, the present value of the first payment will be less than 100K, right? The first payment happens at time n plus 1. So 1 year from time n. So it's going to be 100K discounted of 1 period, right? So the Y is going to be 100K times V. Remember, V is the discount factor. So V is well, 1.05 to the minus 1. So yes, the present value of the first payment is, as you say, less than 100K. But I don't know if that's the question you asked. Now, provided you're happy with this, then we need to do the second part of the question, which is not too bad. You just need to find the right n, right? The n such that the contributions will have accumulated of enough money. The contributions, like those amounts I call C, but also the initial amount. Like he starts, so I call this B0, but in the problem, this is 300K. He starts at time 0. He already has a nice little nest egg of 300K. This will accumulate for n years. But then on top of that, he gets the nice juicy contribution from his employer, which is 17% of his salary minus the tax. Now this accumulates, but you have a formula for that. This part accumulates up to time n, but this is the notation Sn, right? How much value do I get after n years if every year I get a payment of 1? Well, that's the notation Sn, but the formula is this thing. Okay, so in general, if those payments last n years, that's how much you will get. Now, the point is that the unknown in the question is n, and Bn is known. We just calculated how much money he needs at a minimum to retire. So you just need to solve for n. And solve it for n is not too bad here. There's two terms that have n, but you can put them together. Okay, 1 plus I is 1.05, that's fine. Then this one, 1.05 to the n. Yeah, same thing. You can put the c divided by I over there. So in total, you have your 1.05 factor of B0 plus C divided by I. And by the way, I here, I is 0.05, right? I could have put 0.05 here. I just left it I don't know why. Okay, and the other part, minus 1 over I C, you can put it on the other side and so on. And now you have n only at one spot. Should be easy to isolate. You can put it on this side and then you take the log. Okay. As you know, if you have something to the power of n and you solve for n, well, you take the log. That will simplify your life. And that's it. Once obviously ln 1.05 to the n will become n ln 1.05. So you can divide by that and find your precious n. And that's it. Now the last step is, as usual, you plug everything. Careful, this 28,900 is just what I've written before. This thing, the C is 70%, 85% of 200K should give you the whatever number was there, 28,900, and that's it. Now, just careful, you get the n that is not an integer. So what does it mean? Well, this formula kind of assumes n must be an integer, right? Because you accumulate for an integer number of years. Now, if you solve it and you don't get an integer, it just means that we haven't picked number that will give you exactly an integer, but that's fine. You just need to be careful with interpretation. 21 is not enough, because if you plug 21 here, you will get something that is smaller than Bn, right? Because if you solve for exactly Bn, you get a 21 point something. So 21 is not enough. You will have accumulated a bit less than Bn, but 22 is enough. You know that if you plug 22 here, you will get an amount accumulated that will be a bit bigger than the minimum required. So the answer will be 22. The answer will be 22 because again 21 is not enough. Now, in class this morning, somebody asked me, okay, what do I do if I get something that is close to 21, but still, but basically they asked me, what I do if I get 21.1, for example. Now, 21.1, is still not 21, right? So it's the same logic would apply. 21 payments is almost enough, but it's not quite enough. It's not quite enough, so the answer would still be 22. So the point here is just you shouldn't round. You shouldn't round because the question really asks you what's the minimum that is needed to satisfy the requirement. So 21.1 is still not enough, right? So it's not a matter of rounding. Now, I also told them in class, like, okay, if you get 0.01, if that's the answer numerical you get, probably I would accept both, because in this case, I think students might think that, okay, I gave them number that should have yielded 21, so maybe there was a rounding problem somewhere and they didn't get 21.00, they got 21.001. So here I would probably accept 21 as the answer, right? Because it's so close. But if it's not that close, I would need to say, no, no, no. The correct answer is 22. Because again, this indicates that 21 is not enough. They need another year to accumulate, at least this amount. Let me know if you have questions. Like, okay, 3:02. We'll take a break now. We'll come back in 5 minutes with more questions. Yeah, just 5 minute break. So I can rest my voice. And you guys rest, I don't know, your eyes or your ears or your brain. I ask in the chat, how hard was the assignment? Nobody is answering, which, I mean, you can let me know if you want, but I suppose maybe some people don't want to answer because you don't want to say it was super easy if other people found it hard and so on. Someone says it was okay. Last question was a bit hard. Yeah, well, that was intended, right? I needed to give you at least one question that is a bit of a challenge, right? Because I mean, you have okay, people are answering 7 or 8 out of 10. Okay, that's reasonable. That's reasonable overall. Like I need to ask at least one question that is, ChatGPT is probably not very good at doing. I mean, I didn't try very hard with ChatGPT, but I gave ChatGPT the last question and it gave me nonsensical results. I was like, oh, okay, that's good. At least ChatGPT cannot do it one shot. Maybe if you give him or give her, I don't know if ChatGPT is a man or a woman, you give it some better prompts. Maybe ChatGPT can still help you, but at least it cannot do it, one shot. By the way, maybe I shouldn't speak so much about the assignment because it's still open, I suppose, for people with short extension. But I suspect everybody here would have submitted the assignment already. I mean, I imagine, right? I don't know. I think it's fine. It's not like I gave you answers to the assignment. We're just discussing it qualitatively. I think it's been 5 minutes. Okay, so we'll do this question. We'll do it top to bottom because I didn't cover part C and D in the lecture this morning, but hopefully you have a bit of time to do some mortality questions as well. But this question is like a module 4 question, like utility and claims or premiums. Although I suppose premiums applies to module 5 and 6 as well. Okay, so you have a given insurance policy now on which a claim will be lodged, but only with probability Q. So it's possible, no claim is lodged. Now, if a claim is lodged, then the size of the claim is assumed to be uniform. Okay, uniform 0, 1. That will simplify our life a little bit. That's specifically 0, 1. So you can write the total claim amount on that policy as the following thing. X is the total amount. You write it as B, that is a Bernoulli, times U, that is a uniform. Well, yes, because the logic of that is the claim will be non-zero only if the Bernoulli is 1, and this happens with probability Q, which is exactly what you want, right? With probability Q, a claim, well, happens, right, or is lodged. But then if a claim is lodged, you have B is 1. Well, in that case, the amount of the claim, the size of the claim is U. So multiplying B times U gives you exactly what you want. X here, that careful, it's not a fully continuous random variable. It's a random variable that can take the value 0 with probability 1 minus Q. But then if it doesn't take the value 0, then it will be a uniform. Okay, and that way to write the amount of a claim when the claim is possibly 0 is very common, right? Maybe you've seen it in tutorial problems, but if not, that's a very common way to kind of mathematically write this specific situation. And importantly here, you can consider B and U to be independent. Right, so this B and this U are independent random variables. So that's the setup. Now, first question is, calculate the insurance premium of X, so X, the total thing, under the standard deviation principle. Now, remember, standard deviation principle, of course, just says that the premium should be the expected value of the risk plus a certain loading. Now, the loading here, they give it to you explicitly 0.5. 0.5, but times the standard deviation, okay, the standard deviation of the risk, which I might denote sigma x, standard deviation of the risk. So here, not too hard, we need to find expected value of x and then variance of x, and obviously from variance of x, we'll find the standard deviation of x. But first things first, expected value of x, well, write x as what it is as function of b and u. And then you need to remember the property that the expected value of the product of two random variables, if they are independent, is just the product of the individual expected values, right? So you can then split E of B times U becomes E of B times E of U. And that is true because they are independent. Then it's easy. Expected value of a Bernoulli is just Q, the probability of success, the probability of a 1. And then expected value of U, well, the expected value of a uniform 0, 1 is 1 half. Now, of course, I think that's probably clear for most people, but let me just write explicitly that this trick is true, but you need B and U to be independent. For example, if you're trying to find expected value of x squared, for example, you might say, okay, that's expected value of x times x, but this you cannot split. You cannot say, you absolutely cannot say, so you cannot say that this is E of x times E of x, right? Because, well, x is not independent of x, obviously not. They're the same thing. So how can they be independent, right? So you cannot use this trick. You really need B and U to be independent to use this, right? So careful about that. You know, writing E of x times x is E of x times E of x. That's illegal. That's really illegal. If you do that in the exam, I will have no choice but to call the police. Okay, so that's not equal. So now you have the expected value of x. You want to find the variance of x. First, we find the so-called second moment, right? We find the expected value of x squared. Same trick. We can use the same trick. X squared will be b squared times u squared. Those things are independent, so you can take E of b squared times E of u squared. Now, be careful here. E of b squared, they say, well, they in the solution, but it's actually me because I wrote the solution. So I say it's E of b. Now, be careful of that. That's not true in general, but it's true if b is a Bernoulli, just because b takes two values, right? Only 1 and 0. So because of that, b equals b squared. But that's a very, very specific situation where b equals b squared, because of course 1 square is 1 and 0 square is 0. So only because of that, b equals b squared, can I say expected value of b squared is expected value of b. But in general, it wouldn't be true. So that's fine. E of b is q. Now the other side is E of u squared. Now this you need a calculation, but it's should be an easy one. You just use the same formula we've seen in week 1. Expected value of a function of a random variable. You just need to integrate over the bounds of the random variable, but instead of integrating u times the density, you integrate whatever this function is. Like here it's just u squared, right? Well, here it's times the density of u, but the density of u is 1, right? Because we have a uniform. Okay, so we omitted it here. And then integral of u squared, that's the easiest integral we've ever done, will be just u to the 3 over 3. Okay, and then you evaluate it at 1 and 0. And obviously you just get 1/3. So overall you get q times 1/3. Then you're essentially done. You can put the bits together. Variance will be expected value of x squared over here minus expected value of x, which is 0.5q squared. Okay, and then you can put whatever. You can put q in front and simplify it just slightly. Yeah, 0.5 to the square becomes 1/4. Now, lastly, you find a premium, okay, by obviously just taking expected value of x plus half of square root of square root of the variance, also known as the standard deviation, sigma x. And here there's just I suppose it's not entirely necessary, but there's a tiny bit of simplification. You have a q here, but for the variance, right, you have a q in front. You're going to take the square root. So you could write this as, and you have a q as well here. So you could multiply this by q and divide by q. So you haven't changed anything. This way, you can put q squared in front. This will become 1/3q, and this will become 1/4. That's a little bit of a simplification, because then square root of q squared, you can put the q in front, and you have q/2, but you have q/2 over there as well. So it's a little bit of a simplification. You can have q/2 factoring just 1 plus whatever this thing is. Sorry, this thing. And that is your premium. Second question is to find the correlation between x and u, and then briefly interpret the value obtained. So the correlation is the covariance standardized. So usually in most problems, to find the correlation, you first need to find the covariance, and then you standardize it by dividing by the the standard deviations. So let's do that. Let's first find the covariance. Now, careful. Just conceptually, you should realize that it would make sense that the correlation is non-zero because x and u are obviously quite related, right? X is nothing else than a function of u, right? It's u times another thing. But so it kind of makes sense that if you look at this versus just u alone, they should be correlated because they both contain u. I mean, one is u and one is something times u. But then you apply your formula for the covariance. It would be the expected value of the first thing, but the first thing is b times u, right? X is by definition b times u times the other, and then minus the individual expectations multiplied. So the expected value of x times the expected value of u. Then from this line, you use the same trick as before. B and u squared are independent, so it becomes e of b times e of u squared. So that's good. Same thing over there. E times b, sorry, e of b times u becomes e of b times e of u, but now you have e of u as well there, so you have a square here. And that's it. Then you can plug the numbers that you've already computed, right? You already know that, you already know that e of b is q. So e of b is q, and then e of e of u squared will be 1/3. Yes, indeed, this is what we computed over there. E of u squared was 1/3. And e of u is just 0.5, right? Square here. Okay, so you get indeed 1/12 of q. Do we have a formula sheet during the test or just an A2 paper? Well, first of all, it's an A4 paper, right? A4 being the standard format, 1 page. You have the common distribution. You have the common distribution PDF in the test, like you had with the quiz. So that's all you have. You can put whatever you want in your personal page of notes, both sides, and then you have the PDF document called common distributions. And careful, this is not printed in the test. You have it as a PDF attached to your test, because remember, you do the test on the computer. So one of the, I don't know, one of the tabs will be this formula sheet. Well, common distribution sheet. Okay, lastly, we found the correlation. We just, as I said, standardize. You grab your covariance and you standardize it by dividing by the standard deviations, which you already have. Standard deviation of x, you found it before. Standard deviation of x will be the square root of this. Now there's just a bit of a simplification that you put everything out of 12 because it's going to simplify. Like here, if you multiply this bit by 4/4, you'll have a 12 as a denominator, and this one, if you multiply by 3/3, you haven't changed anything. You'll have a 12 on the denominator again. So you'll have the following result. You'll have q4 minus 3q divided by 12. And why you do that is that you have a 1/12 over there, and sigma divided by u. The variance of a uniform is just 1/12. This is this thing over there, right? Yeah, indeed. This is indeed the variance of u, and it's in fact 1/12. Okay, so square root of 1/12, it all cancels the 1/12 over there. So then you get to the relatively nice compact expression here as your final answer for the correlation. And you can interpret it a little bit. So this is an increasing function of q, right? So the higher the q here, the higher the correlation, because, well, numerator increases, but also denominator decreases, right? So you divide by something smaller if q increases, so it'll boost the result. It will boost the final answer. Well, this makes sense because q, you might say, it controls how likely it is that x and u are identical. Well, yes, Q, remember, is just the probability this B is 1. Well, if Q is large, it means it's very likely B will be 1. But if B is likely to be 1, X is likely to be exactly equal to U. And if X is likely to be equal to U, well, the correlation between X and U will be high, because again, X and U are likely to be the same thing. If Q is very small, so if Q is very small, B will be very likely to be 0. If B is very likely to be 0, well, X is very likely to be 0, in which case X and U will not be similar. Okay, in the extreme case where Q is exactly 1, then X equals U. Well, of course, because then B will be exactly 1 with 100% chance. Then the correlation is 1 because, well, the correlation between X and X, or in this case, U and U, is 1. Okay, let me know if you have questions about that. Otherwise, I'll go to part C. So part C is to calculate the insurance premium, let's call it P, again for the risk X, but now under the principle of zero utility. If the insurer has utility function exponential, negative exponential, right? And then P should be a function of Q. P should be a function of Q. So this is kind of a typical utility problem like we've done, well, last week. And well, last week we did a module 6 revision question that was actually using utility, so we did something quite similar to that. It's always the same thing. Principle of zero utility just says set on one side the current utility of the insurer, so that's the utility they have if they don't do anything, they don't sell more insurance. And on the other side, you find the expected utility of their wealth if they do sell insurance. Their wealth, if they do sell insurance, will be increased by P because they collect a nice premium, but then decreased by X because now they have to cover, they have to pay out X, whatever X is. And X obviously is a random variable. Now, by the way, the question doesn't give you the initial wealth of the insurer, but that's irrelevant. I think you might have figured this out already, but if the utility function is exponential, the initial wealth has no impact on decisions. Like it's going to cancel out in the calculation, so the initial wealth is in fact irrelevant. We'll see that in a second. Well, right now actually, so on this side, this is not random, right? It's just V of W0, so you get this. Now on this side, you take, you replace V by the actual expression for the actual utility function. You get the following, the minus, you can put it over there. And then this part is a constant. This part is a constant. Sorry, there's just like a question in the chat. Would B be a zero inflator? I'm not entirely sure what you mean by B is a zero inflator. Well, B is yeah, well, it's an indicator, right? It tells you if B is 1, it means there was a claim. If B is 0, it means there was no claim, right? So I don't know if that answers your question or not, but coming back here, everything that is not random, so this bit is not random, those are just constants, you can put them outside. But as I said, the term that has the initial wealth cancels out, right? Because of course this thing, you put it outside the expected value with the minus here, it's going to cancel the minus there, or the minus e to the minus W0, so you get 1, right? You get 1, the 1 comes really just from e minus blah 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 divided by e minus blah blah blah, right? All of this, well, sorry, there's a minus here as well, so the minus cancels the minus. And that's it. This is a constant. So now you're left with, well, you found the premium as function of this thing, but this thing you need a bit more work to compute it, right? P is log of e to the x, right? So you need to find, well, to calculate this object. Now, this might be a little hard unless you remember your law of total expectation, right? That we actually used last time, I suppose in a similar fashion. Remember, x is just b times u. But now, if b is 0, that simplifies your life tremendously. X will be 0 and the expected value is very easy to compute. But also if b is 1, that simplifies your life a lot because then x will be u, and that's also an easy or relatively easy calculation. So you can then condition on those two cases because each of those cases individually is easy to deal with. So otherwise, you use your law of total expectation to say expected value of e to the x, I'll find it by conditioning on two events that are, well, mutually exclusive and they encompass all the possible cases. B is 0 is one case, and then B is 1 is the other case. Probability B is 0 as, sorry, the event B is 0 as has probability 1 minus Q. The event B equals 1 has probability Q. Then expected value of e to the x, if you know B is 0, well, x is 0 as well, so that expected value is mega e is easy as just 1, right? E to the 0 is 1. Okay, so you're just left with 1 minus Q. I'm just saying this term here is 1. Then this bit, you need just one more step. E to the x given B is 1 is in fact e to the u, right? If B is 1, x is u, so then you need to find e to the u. But e to the u is nothing too hard. You just use your formula for the expected value of a function of a random variable. Again, u follows a uniform 0, 1. So fu is just the constant 1. Easy. So now you're left with this integral, but this integral is easy. What's the integral of e to the u? Well, it's e to the u, right? Because if I derivate e to the u, I get e to the u again. Right? E to the u derivate gives me e to the u. So indeed, that integral is just e to the u evaluated at 1, 0. So you get e to the 1, that's e, minus e to the 0, that's 1. And then it's happy days. You've solved, well, this thing, e to the x. Okay, you can rearrange a little bit. Minus q here, you get a minus q here as well, so you get minus 2q. Okay, and then q times e. Okay, remember, e is just a constant, right? It's a number, an irrational number. I believe it's also a transcendental number, if I'm not mistaken, 2.71 something something. And then, yeah, then that's it, right? Because then you go back to your p. P was a function, well, ln of this thing. You just found this thing, so you're done. That's your p. So you're done finding the premium. Now the last question is, I believe, showing that this premium is a decreasing. Sorry, I'm going too far. Sorry, I forgot that the questions are one after the other, not all with the question. So, okay. Consider P you just computed, right? So the P we just obtained. Show that the ratio of the premium to the expected value of the risk. So you grab whatever it costs to insure this risk under the previous part, right? Under the principle of zero utility. But then you divide by the average, right? The expected value of the risk. This ratio, this is a certain function of Q, right? Show it's a decreasing function of Q. And then can you make intuitive sense of the result? Now, showing it's a decreasing function of Q, that's one part of the question. Then trying to explain why that is the second part. So we'll start with the first part, like the mathematical bit. We need to show that this thing decreases with Q. Now just to ease notation just a tiny bit, E minus 2 is just a constant, right? It would be like 0.71 something something. So we'll just call it C for convenience, right? It's just a constant, right? It's a constant that's positive. Now, P divided by e to the x, this thing over there, is then proportional. So careful here, this symbol, I mean proportional. Proportional, okay, meaning it's equal to that up to a constant. Well, yes, because, well, you can write it in long form. P over e to the x will be this thing over there. ln 1 plus c times q, because I decided to call e to the e minus 2 constant. And then e to the x, well, e to the x, so not e to the x, but ex, expected value of x is q over 2. q over 2. So then, yes, it is just, well, the constant here is 1 over 2 times blah, blah, blah. Okay, so this thing, so now, obviously the constant here doesn't change anything to the fact that this would be an increasing or decreasing function of q. So the goal then is to show that this function, I call it HQ, that's just a name, you can call it whatever you like. You want to show that this HQ decreases as q increases. Now the usual way to do that is to take the first derivative, and if the first derivative is negative, and if it's always negative, you will have shown that indeed the function is decreasing, right? Because if a function is decreasing, then its first derivative, which is the slope of the tangent line at any point, should be negative. So let's see. First derivative. Okay, well, how do we do this? Well, you can use the formula for the derivative of a ratio. So, well, yeah, derivative of this will be 1 over 1 plus QC, which is there. Then times derivative of what's inside, that will be C, but then times the second term, which is Q. So you get QC here. And then minus the first term unchanged. So ln 1 plus Q unchanged, but times the derivative of the second term. Second term is this one. Derivative of Q is just 1. That's fine. And then you derivate everything. Sorry, you divide everything by the denominator squared. Okay, so here, this is just usual rule. The usual rule for the derivative of a ratio. Okay, now the problem here is that unfortunately, you would like this to be negative, but it's actually not obvious if this quantity is negative or not. Like, unless maybe you're some sort of math genius that sees something I don't. When I look at that, not really clear if this is going to be negative or not. Like, because ln of 1 is 0, but ln of 1 plus something will be something positive, right? But then this will be positive minus something positive. I'm actually not sure if it's going to be positive or negative, right? So there's a bit more work to do to show that this thing here is indeed negative. Now, one realization that might help us is that the denominator is always positive, right? Q square is always positive. And also, Q times C is strictly positive. Well, Q is strictly positive and C is strictly positive. So we can simplify a little bit the problem. The question of is this thing negative is equivalent to the question, is this thing negative, right? Because obviously dividing by a positive constant doesn't change the sign of a value. Okay, and again, we can just make, this is just to simplify the notation a little bit. You can denote QC, QC, QC by just X and note that X is strictly positive, right? Because QC is strictly positive. So then you have a new problem you're facing. That's your new mission. Show that this is negative. Show that this is negative. Which again is not obvious because this part is positive. This part is positive. It's bigger than 1, sorry, and then ln is bigger than 0. So you have something bigger than 0 minus something bigger than 0. It's not immediately obvious if this thing is always negative or not. But now, how do you show that this is negative? Well, you'll derivate again. Now, first thing is, this new function is in fact equal to 0 if you evaluate at x equals 0. Now, our support for this function is x strictly greater than 0, but we notice that if here you plug 0, this term is 0, and here if you plug 0, ln of 1 is 0, so you have 0 minus 0, you have 0. And then, well, I'll go to the steps in a second, but if you derivate this function again, then it's going to be clear the derivative is negative. But so what this means is that at, so this is, if this is x, at the value 0, this function I called f is equal to 0. But thereafter, fx is negative. So if the derivative of x is always negative past 0, well, you know it's a decreasing function. Well, if it's a decreasing function that starts at 0, it will be negative everywhere. It has to be. So that's the logic of the solution. Now we just need to do this. We just need to derivate this f, which is not too bad. Again, derivative of this bit. If you use the again the rule for derivating a ratio, you should get to that. Yeah, let me know if you disagree. And then derivative of this, same thing. It's just going to be 1 over this, 1 over 1 plus x. And then that's good. You can put 1 over 1 plus x in front. Then this one is squared, so you get 1 over 1 plus x. And then this becomes 1. And now finally you can unambiguously conclude, because if x is strictly positive, then 1 over 1 plus x, this will be strictly smaller than 1. This part will be strictly smaller than 1. So something smaller than 1 minus 1, this whole thing will be strictly negative. Something strictly negative times something strictly positive will be strictly negative. Oof. Okay, so that was not that obvious, but provided you agree with all those steps, now you've shown what you wanted. You've shown, you've shown that this thing has to be negative. This thing has to be negative. Yeah. Let me know if you have questions about that. But now let's go back to the interpretation. What is this? What is this quantity? Well, it's simply the premium, but expressed as a fraction of the expected value of the risk, right? So it's how much bigger is the premium compared to the expected value of the risk. So how much more is the insurer charging compared to the expected value? Like, for example, if this ratio is whatever, 1.2, what means the premium is 1.2 times bigger than the expected value, right? If this thing is whatever, 1.8, well, then the premium is 1.8 times bigger than the expected value of the risk. So in some sense, you might say the insurer is charging more. They're overcharging because they're charging a bigger fraction of what the average risk is. But we're saying this thing decreasing as function of Q. And that, when you think about it quickly, it might not be so obvious, because remember, Q is the probability of a loss, right? So Q is the probability there's actually a claim lodged. So in some sense, you might think, okay, if Q increases, that should increase the risk. Well, it increases the risk, the size of the risk in kind of absolute value, but it does not increase the size of the risk relative to its expected value, because of course, the expected value of the risk is function of Q, right? It's just Q over 2. Just Q over 2. So here, you have to be a bit careful when you interpret. That's not, this quantity that decreases as Q increases is not the risk, is the ratio of the premium to the average size of the risk. And yes, here I think it makes a lot of sense. It decreases as function of Q, because if Q is very large, it means you expect a claim, right? If Q is very large, you expect a claim. So the fact there's a claim is not unexpected, right? It's not a surprise. If Q is very small, well, it means usually you don't expect a claim, because the chance of a claim is small. So in some sense, there is more uncertainty when Q is small, because again, a small Q will mean that when a claim does arise, it's not expected. It's a surprise. And obviously here, the insurer is risk averse. The insurer is risk averse because they have a concave utility function. I think you know that e to the minus x is a decrease. It's an increasing but concave function. So the insurer is risk averse. They don't like uncertainty. And a small Q means when we get a claim, it's a big surprise, so it's more uncertain. And because of that, then yes, I think it makes sense that to compensate for this risk, they will ask for a bigger premium as a function of what the average risk is. So I don't know if that makes sense at all. I believe that's more or less what those explanations say. I can show them or review them quickly, but yeah, if Q is small, getting a loss is a big surprise since the insurer would not expect it. However, if Q is quite big, then they would be expecting a loss, right? In the extreme case, if Q is 1, well, there's no uncertainty at all about whether a loss or not will happen. You know for sure there's going to be a loss. So in some sense, there's less risk there because risk has to do with uncertainty, right? Not knowing ahead of time what's going to happen. If Q is 1, you know ahead of time, you know for sure there's going to be a loss. Okay, if you want a more mathematical reason, try to compute this thing, right? The coefficient of variation, right? Now, the coefficient of variation is a sort of scale-adjusted measure of risk. Is the variance of the risk, but scaled or divided by its expected value. Now, this thing is very easy to compute. You'll find it's also a decreasing function of Q, right? So this whole thing, obviously, it's a function of Q, but then it's also decreasing as Q increases. So then the same logic applies. If the standard deviation as function of the expected value decreases, it points to the same thing. It points to the fact that relative to the average size of the risk, the variability of the risk decreasing or decreases for larger Q. Okay, so this again confirms the idea that Q is less risky for the insurer. Okay, if you don't have any questions about that, I'll go to the next question now. We have only 10 minutes. So there's 2 more questions. They're both about mortality. Maybe this one. Okay, in 10 minutes, I definitely don't have time to do question 5, but I do have time to do question 4. But don't worry, question 5, I've done it this morning. So if you want to double check the answers for question 5, you can check the recording from this morning. For now, I'll do question 4. Maybe I can do it with you because it's a multiple choice question. So I'll go just to the, not to spoil the fun, I'll go to the version of the question that doesn't have doesn't have solution. Okay, so here we remind you of actuarial notation. So we say AX is a life annuity, right? The expected present value of a life annuity if somebody is age X. Now careful, AN is not a life annuity, right? A with the symbol corner, N is the present value, which is the regular present value of a regular annuity of N certain payments, blah, 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 right? I is an interest rate, X is the age of a person, N is an integer. Further assume that those things, well, anything in the question AN and PX are computed using male mortality, right? So AX, PX, they're computed using male mortality from the Australian life table, right? That's a life table we've seen in class in module 5. However, if we add a star to those symbols, AX star, PX star, it means those quantities are computed using the female life table. Now that's the context, so we just use standard notation, and a star means the female life table is used. Circle all the identities below that are true. So maybe I ask you to do a bit of work now. Let me know which one you think are true. So A. Is A true or false? Yeah, thumbs up. Yeah, true, indeed. Indeed, that's directly a formula we've seen, right? In week 3, financial mathematics. To get the annuity due, you just multiply the annuity, the regular annuity by 1 plus I. Okay, so that's the formula we've seen. B, maybe not as obvious. Do you think B is true? Okay, nobody has answered yet. People are less confident about B. Somebody has put a thumbs down. Somebody has put a, two people have put a thumbs down. I'm sorry to say, but okay, 3 thumbs down, 2 thumbs up. Unfortunately for the people who put thumbs down, okay, now they've corrected themselves because of the tone I've adopted. It's in fact true. It's true, but it's not as obvious. So you need a bit of work to convince yourself this one is true. Do a timeline. With those financial maths problems, doing a timeline is usually a good thing. So A double dot N means that you have a first payment of 1 happening right now, right? But then you have another payment at time 1, another payment at time 2, blah, blah, blah. But because the annuity is due, at time n, you get nothing, right? But the last payment is at time n minus 1. But now, what is the meaning of A without the dots, n minus 1? Well, the meaning of this one is getting a payment, the first payment 1 year from now, so this one, and then this one, and then this one, blah, blah, but only n minus 1 payments in total. So the very last would be indeed this one. So of course, this is not equal to this, but the only thing that's missing, okay, again, A n minus 1 is this payment, this payment, this payment, this payment, this payment. The only thing that is missing to get to A double dot n would be this one, this little guy, this little one, which is here. And so indeed it's true. Okay, it's true, but you need to think about it a bit more, right? It's not so obvious. Let me know if you want me to explain this again, but otherwise I'm gonna ask you, is C true? Do you think? No. Okay, so one person says no. Indeed, it's false. It's false now. Why is it false? Well, we haven't seen such formula, right? So when we haven't seen a formula, the default assumption would be it would be false. But sometimes this we haven't really seen this, but this you can put the payments on a timeline and then realize it's actually true. But this one, there's no way you're gonna find that it's true, right? You can try. Like I think there's 2 ways to kind of show that it's not true. I mean, the formula we've seen that links ax and ax plus 1, actually we saw a formula that links ax double dot, right? And it was ax. We've seen that, okay, this one you get a payment for sure, and then the reasoning was if the person survives, then they will be age x plus 1. They will be age x plus 1. So they will get the payments that they are entitled to get at age x plus 1. But it's 1 year from now, so you need to divide by v, right? So that's the formula we've seen. So you could try to replace ax double dot by what it is as a function of ax, but when you do that, you're not going to get this formula. But also, you can try to make the same reasoning for ax, not ax double dot, right? So what would be the reasoning? ax alone, how can you link it to ax plus 1? Well, ax, the first payment, this is a life annuity, but the first payment would be at time 1 if you're still alive. To get the payment, you need to get to that age, right? So you need to survive 1 year. If you survive that year, you will get a payment of 1, and then you will get all the payments somebody age x plus 1 will get. But you evaluate this at time 0. So this would need to be discounted of v. This would need to be discounted of v. So the real formula that would be true would be this one. Okay, which of course is not there. It's not true because you don't have the v here. Now part D. Do you think it's true? Part D. Part D, three people are saying yes, but they all fall in the trap because this A is true, but careful. Now we have life annuities. We have life annuities. So there is no such formula for life annuities, right? This one is actually false. Now, luckily, there's part E that might help us to catch our mistake in part D, right? Because part E is true, right? We have seen this formula for life annuities. For life annuities, because the payments they last forever, no, not forever, they last for as long as you're alive. Hopefully you live forever, but the payments last for as long as you're alive. So AX is just the first payment you get for sure, and then it's all the payments you get under a life annuity that is not due, right? So this one is true, and this is written in the slide. But now, if this one is true, this one cannot be true, right? Because this one cannot be true, because then if you simplify this one, you get AX plus, plus AX times I. Well, AX times I, there's no reason it would be equal to 1, right? Why would AX times I be 1? There's no specific reason that would be true. So if E is true, which it is, then D shouldn't be true, right? Okay, now, sorry, it's 54. Look, I'm going to finish this question. If you have to go, you have to go, but I'll just, for the sake of having a complete video, I'll finish this one. We're up to F. Is F true? Thumbs up or thumbs down in the chat. Thumbs down. Yeah, indeed. F, I don't know why it would be true. Like, you need to try to understand the meaning of the formula. Here, obviously, we haven't seen a formula like that, and the formula doesn't really make any sense. Like, because this part is probability to die in the next 2 years, right? But then this part is probability to die times you now age 1 year older and you die again, right? So it's strange. Like, I don't know what this probability represents. This literally says probability to die and then die again, right? So that doesn't really make sense. It wouldn't be equal to the probability you die in the next 2 years, right? So this one is false. What about G? G people say true. Now, G, I have to say, is maybe a little bit of a trick question. The logic here is a bit better in the sense that, okay, probability to survive 3 more years would be probability to survive 1 year, then survive another year, then survive another year. But remember, those probabilities, they're assumed computed from an actual life table, right? And in reality, as people get older, they age. So px is not equal to px plus 1, right? So G is actually false because this assumes mortality doesn't. This would be true if mortality doesn't change, right? The probability to survive age 40 is the same thing as survive age 41, is the same thing as survive age 42, right? So while, this would be a reasonable approximation of this one, strictly speaking, they wouldn't be the same. They wouldn't be the same because, again, I'm just giving a specific example, but P40 is not exactly equal to P41. It's not exactly equal to P42, for example. What about H? Now we're trying to use the age, the specific ages. So probability to survive 2 years is this one times this one. Somebody says thumbs up. Somebody says thumbs down. So yes, this is another kind of trick question, I suppose. This is false because it's not the right ages, right? This would be a probability somebody age X now survives 2 more years, but this would be then, it should be, well, the real probability would be you survive 1 year, so you're age X and you survive, and then you reach age X plus 1, and then you survive again, right? So the real relation is this one. So this is kind of offset. This is offset by 1 unit, right? Like this would need to be X to be true. So it's false. And then I, remember the star means female. Okay, true. Yes, indeed true. At least in the Australian population, but this is true pretty much everywhere in the world. Females on average live longer. So a life annuity, something that pays out payments for as long as somebody is alive, would be more expensive for a female. So that's true. Yeah, this would be bigger than this because females live longer. On average, they get more payments from a life annuity. This kind of logic is applied to the other ones, right? So to wrap up here, P20, is it bigger than P20 for a female? No, that's false because males die more, right? Males die more, so their probability of survival, of course here P is the probability of survival, would be less than that of a female. So this one is false. P40 bigger than P30, again, false because, well, older people die more than younger people. So the probability of 40-year-old dies, unfortunately for them, is higher than probability of 30-year-old dies. So probability of survival for a 40-year-old would be smaller than probability of survival of a 30-year-old. And lastly, same sort of logic. L, well, I'll ask you. Let's finish with that. Is L true? We have one thumb down, two thumbs down. Indeed, that's false. That's false. Same logic. If somebody is older, they have on average fewer years ahead. So an annuity for somebody older would be cheaper than an annuity for somebody younger, right? So the relation would be like that. It's more expensive to get an annuity for somebody younger. They're going to live longer, well, on average. Okay, I believe I'll stop here. I would say don't neglect question 5. Unfortunately, I couldn't get to it, but I think it's a very good revision question for mortality things as well. And it's also slightly cheeky. It has a Josephine and Josephine grandma is there in the question. I recommend you cover this question in your own time. Again, if you want to double check your solutions, check the video I recorded this morning with the morning class. I've covered this question in detail. Okay, so I'll stop here. Thanks so much for your attention. As usual, I'll stay in the chat a few moments in case anybody has questions. So thank you very much, and hopefully see you tomorrow in the last lecture. It will be a bit sad, but such is life. Okay, let's have a look at the longer question. Okay, now Josephine apparently has siblings in this question. So Josephine, Johan, and Josiane are sisters. They all started a 4-year degree. 4-year degree. The probability any one of them individually graduates is 70%. Individually. Now the grandma of the sisters is age 80. She will reward any granddaughter who graduates with a payment of $10,000. Okay, thank you very much, grandma. Payment is made to a given granddaughter in exactly 4 years, right? So they need to graduate to get it in 4 years. But only if the granddaughter graduated and grandma is alive, right? So unfortunately, if grandma doesn't make it to age 84, granddaughters get nothing. That's not funny. Also, unfortunately, grandma is a chain smoker. Bad habits. So she has a high mortality that is captured by this life table. Okay. So yeah, this table, yeah, those numbers, they're higher than like real mortality for people that age, and at least in Australia, right? Okay. The 3 sisters cannot die. They follow all the newest TikTok health trends, so they're fine. I could have made the sister possibly die, but then it complexify everything. And anyway, the chance they die is quite low because they're young. Okay, consider all the events in this question to be independent. First question, what is the probability grandma pays out exactly 20K in gifts 4 years from now? So that's more a probability question, but you need to be able to, yeah, question?
We assume Josephine has a lower graduation rate with her
Can you assume Josephine has lower? No.
Because we know that. Yeah, but she goes on a date like every week, and she has like severe binge drinking problems. I don't think that's necessarily helpful to graduating.
Well, you don't know it's the same Josephine, right? Like, I think. Well, I know you're just messing around, but each question is independent, right? You can't. And that's actually, I think it goes without saying, but that's true for the test as well, right? Like, there's lots of Josephine questions in the final exam, but of course, you shouldn't. It's a new Josephine each time, right? Because otherwise, it would be messy, right? You need to use the information in question 1 to do question 11, because Josephine is coming back again. Obviously, within a question, right? Part A, part B, part C. Obviously, it's the same Josephine. Otherwise, it ain't. But no, all the sisters have 75%, and you know it's okay. They go on dates, but that's part of life. You know, you can't study all the time. Maybe I'll go to the solution file, but how do you solve the first part conceptually? How can she pay 20K in gifts? Two sisters can well need to graduate, but also she needs to be alive, right? But of course, those events are independent, so it's not too hard. Okay, you need to find probability exactly two sister graduate. Okay, that's really a binomial, right? Number of sisters who graduate really is a binomial. Now it's easy. You only have well, this you could say it's choose 2, 3, like choose the two sisters out of 3 that will graduate. Probability of one of those cases, 2 of them graduate, 1 of them doesn't. But then you multiply this by the probability that grandma makes it to graduation, right? Okay, so then that's it, right? Like, and obviously we use independence of event, right? Probability that 2 sisters graduate and grandma is alive. If we say those are independent events, well, you multiply them. Now, how do you find probability that grandma is alive? You use your life table. Just careful. If she's exactly 80, that number will be the denominator here. Okay, and then survives 1 year, 2 years, 3 years, 4 years. So the numerator will be this one. Okay, number of people still alive at age 84. The logic is clear? Okay, so sorry, I'm trying to hide the solution. Next question is, what is the expected, well, total expected present value of all gifts made from grandma to the 3 sisters? You can use an interest rate of 6%. Total expected present value of all gifts. I think you might read this question and think it's quite hard, because you might think, I need to find all the probabilities that, you know, exactly 0, exactly 1, exactly 2, exactly 3 get the payment. But in fact, it's not so bad, because we're looking for expected value. Your expected present value of all the gifts would be the expected present value of the gifts to one specific sister, plus expected value of gifts to the other, and so on. So here, I think it's going to help you quite a lot to realize expected present value, all gifts, will be 3 times expected present value of gifts to one sister. Has to be. Is that clear? Okay, so if you realize that, then it's not too bad. And there's not many random events to consider, right? there's just a random event that the one specific sister graduates and grandma is alive to, well, to pay out. All right, so we're at time 0. At time 4, like it's exactly like in the, well, it's the logic of the same previous question. Payment happens to a given sister only if you need 2 things, right? You need graduation of the sister and well, and survival of the grandma. Okay, so here, if you want a formula, you can say, okay, we need the probability of a payment at time t, but in our case, t is 4. That's the actual, CT is just a notation for the actual amount. Okay, that's just a 10K. And then you don't forget discounting. Of course, you discount to 4 years. And that's pretty much it, right? A payment happens if sister graduate and grandma is alive. Okay, so you get whatever this number is, 4,000 something. And lastly, of course, you have 3 sisters. So in total, 12,000. 12,000. Is the logic of the solution clear? It's always probability a payment is made times the actual payment times whatever discounting you need. And probability times actual amount if the event happens, the event that triggers a payment, I mean, times discounting. Questions? Okay, the next part. I think it's my favorite part. Grandma is an older sister. Okay, let's call her auntie. Now, she's currently age 82, right? So she's exactly 2 years older than grandma. Now, auntie has similar bad life habits to grandma. Now, you have it on good authority that the expected remaining lifetime of auntie is 7 years. 7 years. Given that, what is grandma's expected future lifetime? And they tell you, so that's what you need to solve kind of mathematically, but they say your calculations may rely on reasonable assumptions, but you must state and justify such assumptions. And also explain if you think your answer is an over or underestimate of the real value. Okay, so grandma is age 80, her sister is age 82, and her sister has expected life expectancy remaining 7 years. How do you go from that to grandma's actual life expectancy? Any ideas? Yes?
Maybe the probability that she survives to 82 times the expected value once she gets to 82.
Something like that. You say probability she survives to 82 times expected life expectancy when she gets there. Yeah, that's the logic of it. I think in words you're saying we should use the law of total expectation, right? Expected value now at age 80 would be probability she makes it times expected value at age 82, but also plus, you forgot a bit, probability she doesn't make it to age 82, but then she's still going to live a little bit more, right? So yes, that would be the way to do the question, I would say. Yeah. Now, but if you do that, there's kind of two approximations you're going to make. Well, okay, the first reasonable assumption we can make is that auntie's mortality is also captured by the life table provided. Well, this is reasonable because 2 sisters would have similar genetics, and the question explicitly states that they have similar life habits. So basically we're saying if grandma reaches the age 82, then she will, at that age, have the remaining life expectancy Auntie currently has. Okay, 7 years. But obviously, that's a conditional statement. If she makes it to age 82, then she will have 7 years left on average. As we said, the mortality in this life table is quite high, so the probability she reaches age 82 is not that close to 100%. And then, how can we mathematically then relate this? So, well, specifically for us, expected value of, remember this symbol Tx means remaining lifetime of somebody age X, but for us, what we're after really is E of T80, right? Expected remaining lifetime of grandma, who is age 80 now. So we want to relate that to this one, and this one we consider that we know it. We consider that, okay, this one would be 7 years, expected remaining lifetime of somebody age 82. As proposed by the gentleman over there, we'll use the law of total expectation. And here we can just, what makes sense is to condition on the event, grandma survives the next 2 years. And again, how to know what event to use in the conditioning? Well, you need to use the context of the problem. If you know she survived 2 years, then her expected life expectancy is known. So the problem becomes easy. Okay, so law of total expectation. This expected value would be expected value of Tx knowing she survived, times the probability she survives, and then expected value of her remaining lifetime given she did not survive. Okay, so now careful here, don't forget the 2. Right, 2 plus whatever this is, expected value once she reaches age 82. This is 7. Yeah, you need a 2 there because we're at time 0. Currently, she's age 80. If I know for sure she'll survive, her average remaining years will be those 2 years that are for sure she survives 2 years, and then she'll be 82, and then she'll have 7 more years on average. Does that make sense? All right, so if you know for sure she's to survive at least 2 years, then her life expectancy right now is 9 years. Okay, well, probability she survives, that's easy from the life table, L82 divided by L80. Okay, so you see she has 88.6% chance to survive 2 years. Now, the bit not to neglect as well is this one. Expected remaining lifetime if I know she doesn't survive. So I condition on S complement, right? S complement would mean the event she dies in the next 2 years. Now, I replace this by 1. I replace this by 1, which is one of the assumptions I need to make, I suppose, because I'm saying times 0, now she's age 80. Time 2, she would be age 82 if she makes it. But the event here, S complement, is simply the event she dies at some point in that time interval. Okay? At some point in that time interval, she dies. Okay, at some point, but I don't know anything else. I don't really know anything else, so I'm making the approximation. Okay, if I know she's going to die between time 0 and time 2, on average she would live 1 more year. She would die at some random point in that interval. Okay, on average she'll live 1 more year. That's an assumption, or a reasonable assumption to make. Okay, and then you compute this, you get 8.08, and you see, I initially thought this is quite low because if she makes it 2 years, she has 7 more years. So I would have thought this would be closer to 9 than, to 8. But I think it makes sense in light of the fact, okay, she's actually reasonably likely to die next year or the year after that. Right? So she only has 8.08 on average remaining years. Is the calculation clear? Okay, now we can comment a little bit on the reasonableness of those assumptions. Okay, we estimate that if you know she survives, her expected lifetime will be 9, 2 plus 7. This is quite reasonable, but you might say something like, there's improvements in life expectancy over time, there's improvements in medicine, so you might say something like, when she reaches 82, will be 2 years in the future with like a bit more medical advancement, maybe she'll have a slightly better prospect than her sister had when she was 82. Okay? But frankly, 2 years is a short period to have lots of medical advancement, so the effect is negligible there. Okay? You might say her remaining lifetime, if she reaches 82, might be slightly higher than 7 in reality, but that's a small effect, right? So you might say something like, okay, this number based on that is maybe a very slight underestimation. Does that make sense? Now, the second reason, frankly, is quite subtle, so I don't think I would necessarily expect you to come up with this in the test, but let's still review it. It's this part here. Approximating her future lifetime as 1 if she knows she dies is almost certainly a small underestimation. It's almost certainly a small underestimation. The reason for that is that, well, here what we know is just the event we condition is survive or no the next 2 years. So the information we have is she will die in the next 2 years. That's it. That's all you know. But people tend to die older than younger. Okay, maybe aside the first year of life, which is quite risky when you're a newborn. After that, mortality increases over time. So people are more likely to die older than younger. So because of that, if you have a time period of 0 to 2, and I tell you, okay, she's going to die at some point in that period, but that's all I tell you, it's still slightly more likely she's going to die towards the end of that period. Because that end of that period has a slightly higher mortality than the beginning of the period. If you're not convinced by this, take a bigger time period, right? You know, I tell you, like somebody in my family, they were alive at age 40, but then unfortunately they died before they reached age 60. Right? Would you say their life expectancy from 40 was 10? Probably not, right? If I tell you they died at some point between age 40 and 60, you would probably guess they died in the second half. They died closer to 60 than 40. Because again, people tend to die older than younger. Right? That's kind of obvious if you take a very long time period. At a smaller scale, only 1 year, or 2 years here, it's still true, but obviously the effect is small. Now, if you're not convinced by that, you can actually make the calculation. You can compute this. You can compute, so basically what I'm saying is, if you know she died between time 0 and 2, and that's all you know, she's a bit more likely to die in this part than die in this part. Because of that, her expected lifetime will not be 1, it will be on this side. It will be slightly bigger than 1. And you can make the calculation, what's the probability she dies in the next year if I know she will die in the next 2? So she will die in the next 2, I don't know when, but what's the probability specifically she dies in the first year? Well, that's just a conditional probability, so it's not hard to do. Here, well, we use, well, this is then just probability she dies in the first year. Well, and she dies in the second year, but dying in the first year and the second year becomes just probability she dies in the first year. over probability she dies within 2 years. Sorry, I'm skipping the subscript for the age, like this is 80. Okay, conditional probability, you can find this one, you can find this one. Plug your numbers. You'll get roughly 48%. So less than 50%. Okay, so said otherwise, this confirms what I said qualitatively. She's more likely to die in the first year. Now, this is true here because those life table numbers, they're actually real numbers I took somewhere. I forgot where I took them, but they're a real life table, just an old one. Or maybe it's a recent one that I boosted the mortality on purpose. I forgot what I said, what I did, because I wrote this life table a couple years ago, and I've been reusing it for different questions. Does that make sense? Okay, so because of those two reasons, this number will be a slight, okay, but slight underestimate. Now, I can't tell you by how much, but it's definitely slight. Her real life expectancy is not 8.5, for example, right? It might be, I don't know, 8.1 maybe. I think my handwriting is getting worse over time. Maybe I'm getting old.